Hi, folks. My name is Daniel Hardman. Welcome to a presentation about high availability. If you saw me come in the back of the room there just a minute ago, we had our own little high availability moment, whether Daniel's going to be highly available for his own presentation. It all worked out. So my name is Daniel Hardman. As I said, I'm the Chief Solutions Architect at Adaptive Computing. I've been with Adaptive not for very long, about 6 months. My background in industry is mostly in enterprise software and cloud computing. So I'm a little bit more of a newbie on the HPC side. I began learning HPC as I came to Adaptive. I worked for years at Symantec, for example, on their backup exec product line. Have some background in storage and networking. Also ran a startup social networking startup, and have some experience with big data. Yeah. So is this line safe? Yeah. Okay. So some of the stuff that I'm going to share with you today is not my own ideas, but rather stuff that I've gathered from our professional services team, and I'm functioning as a spokesman. I'm happy to take questions, and I think I can answer a fair number of your questions, but there may be questions where I'll say, I'm not the expert, and I'll refer you somewhere else. There's also a white paper that goes along with this presentation. There's some copies of it here that are printed right up here in the front. And you can also download a copy of the white paper, and there will be a hyperlink at the end of the presentation to where you can get that. So let's talk for just a minute about what we're trying to accomplish today. This is what we're trying to accomplish, right? I'll give you a chance to read about Asoc the intern and his misadventures. And good old Wally giving him really good advice. So I don't know how many of you have actually had an experience like this in your career where you accidentally deleted something and then panicked and so forth, but I think it should be a little bit eerily real to all of us. We know that data can disappear. Poor Asoc gets a little bit carried away with himself, and I'm not sure why it says February there on the end, but basically, the pointy-haired boss smashes the laptop over his head and says, "Leave me alone." But anyway, that's not really what we want to do with HA, right? We're not just trying to blame somebody else. We're trying to keep our systems up. This is probably a good summary of what we're really trying to accomplish in HA. We want to eliminate or reduce downtime for running jobs, and I'm going to talk a little bit about what we mean by downtime in just a minute. We want to make sure, besides having our running jobs keep running, we want to make sure that new submissions remain possible at all times. We want to make our failovers visible and manageable. So it's nice if the failovers are transparent to the end users, but the admins need to know that they happen and be able to control what happens when they happen. We may have to satisfy regulatory requirements or SLAs. They're similar in a lot of ways in the kind of constraints they impose on our solution. And we also need to preserve an audit trail in many cases so that we can understand what has happened to the system over time. There might be some other goals. I'm not claiming this is an exhaustive list, but a pretty good summary, I think, of the basics of what we're after. Now, one thing that we have to understand is that HA costs time and money. And so we have to make some calculated trade-offs about how much of that time and how much of that money we're willing to invest in solving a problem. Certain kinds of eventualities are easy to plan for, others are hard. And so I've listed a few here. Some of these should not intimidate us too much. I mean, it should be pretty straightforward for us to plan for power outages and software crashes. But as you move down this list, these get increasingly hard to cope with, right? I don't know how many of you followed the little news item about the Chinese army being accused of organized hacking. Hey, These are smart people that are very sophisticated and planning how you're going to keep your system up if somebody really attacks you with that kind of intellectual horsepower. That's not a trivial task. Maybe some of you were interested in that meteor that went over the Ural Mountains a couple months back. If one of those had hit your data center, okay, now this is a little bit harder thing to plan for. You might still want to plan for it, but you have to decide how much risk am I willing to just live with versus how much do I try to drive out in advance by spending time and money on it. Probably none of us would plan for that last eventuality, right? The meteor that killed the dinosaurs. If that happens to us, I think we'll have bigger problems than whether or not our data center's up. But you never know. I mean, you can make whatever calculations your business decides are the right ones. Now, let's talk about that word downtime. What exactly do we mean by downtime? Let me give you a little scenario here. Suppose that at time 0, we experience a hardware failure. So 3 minutes after this hardware failure, the system is back up, possibly because of heroics, possibly because of wonderful planning we did, whatever. The system is back up in some sense. I've called it usable but very slow. So perhaps the most critical users of the system can get something done, but a lot of the other users of the system are kind of locked out still. And then maybe 10 minutes after that, we've done a full restore. Everything's peachy again. Except, we discovered that 30 minutes before the hardware failure, one of the checkpoints that we did, well, actually, several of the checkpoints we did during this gap are not fully trustworthy. We're not really confident in them. The first point that we can really be confident of is a checkpoint that we took 30 minutes before this event. So how much downtime did we really experience here? Okay, I think there's more than one valid answer to that question, and it depends on your business. You get to decide how you want to define downtime. You could say, well, it's just this time right here. I think a lot of us probably would not pick that one, but there might be some businesses that would. You could say, well, it's this time right here. It depends on what's in that checkpoint and how critical it is to the success of your business. I think a lot of us would pick this longest one, right? We'd say that's 43 minutes of downtime. But anyway, it just depends. I'm not arguing for one definition or another, just saying that you have to understand that. And when you're planning an HA strategy, you have to be very clear, including with business owners who aren't necessarily prone to think about the technicalities here. You have to explain to them how you want to define downtime and what your real goal is. Fair enough? So I'm going to cover 4 basic recipes that you can use to build highly available deployments of Moab Stacks today. These stacks could be in the HPC world, or they could be in a cloud. The same general principles apply in both cases. And these recipes are not exhaustive. There's other ways that you could do this too. But I hope as I cover these 4 basic ideas, you will get a sense for what's possible, and you'll get some comfort level about what kinds of trade-offs you might make. Now, it'll hopefully also be clear to you what are some pros and cons of each one. Why might you want to choose one? And also, I want to make sure I give a minute to Bernhard to talk about how this relates to state-of-the-art for other competing software stacks out there and how they might solve the problem. So let me start with this really simple one. We call this simple built-in HA because it takes advantage of features that are built right into the product itself. So a feature right in Moab, a feature right in Torque. This is fairly simple, and because it's simple, we're going to start there. You'll see immediately some things that are wrong with it for certain use cases, but some things that are good about it too, I think. So with simple built-in HA, what you're building is a hot-warm system. You have 2 systems. The daemons on the fallback server are idle. They're running, but they're not really doing anything. And in Moab and Torque, you use a shared file system. You have synchronized clocks between the 2 machines. and you use the last mod date on a semaphore file to tell whether a machine is the primary or the fallback server. I'll explain how that works in a second. MAM can also be used in this kind of an environment. MAM has some built-in HA features. For example, MAM's command line client can automatically work with both a primary and a fallback server so that you can run commands and, transparently fall back to one if the primary is unavailable, and use the database replication of your DBMS. This is what the deployment actually looks like. You have some kind of a virtual IP address or load balancer that fronts the client requests. They come in and the requests are forked over to whichever machine is currently active. You have Moab and probably PBS server running on that head node here. And then you have a shared file system. And you see a bunch of files here. These would be configuration files and whatnot, license files. And whichever of these two machines starts up first, opens up the files and starts writing to the semaphore file. Every few seconds starts touching the semaphore file saying, okay, I'm still alive, and the last mod date on the semaphore file then functions as a sort of a heartbeat. The second machine that starts up, you see dotted lines around the Moab and torque triangles here. These are actually running, but when Moab starts up, it looks and says, when was the last mod date on my semaphore file last changed? Oh, it was only changed seconds ago? Well, somebody must be actively maintaining that. They must be the primary, therefore I'm the secondary guy, and so I'm going to just go into wait and see mode. So every few seconds, this Moab will check the file system and say, hey, what's the last mod date on this file? And as long as it's hardly in the past at all, a few seconds back, it'll remain inert. But if it goes stale, if it says, oh, it's been 30 seconds or a minute since that file's been touched, that must mean that machine 1 is dead. So I'm going to become active now, and away I go. Torque has exactly the same mechanism going on. Okay, now, if you're thinking about this carefully, you'll see some weaknesses in this system. Nobody's claiming that this is perfect. It does have some advantages, though. First of all, it's fast and easy to set up. And secondly, there's not a whole heck of a lot of a learning curve. Now, depending on what kind of requirements you have for your environment, that might be good enough. I'm not advocating that you do it, though, if you need more fancy guarantees. Some of the cons here, if you have a solution database, if you have web services, if you have a portal, we're not protecting those parts of the stack, and that's a problem. This also depends on synchronized clocks between your two machines, and that's a little bit of an iffy proposition. I mean, certainly you can synchronize clocks, but keeping them synchronized across the same kind of events that make a network brownout happen is a little bit trickier than it sounds. And it also depends on the shared file system propagating the metadata about files in a reliable fashion, which is also not always predictable. There's a risk because of those sensitivities to false triggers, and that can be a problem. And depending on what kind of shared file system you use, that can be a single point of failure. So, pros and cons. Any questions about this? Okay. Bernhard, maybe you'd like to talk a little bit about LSF. You have some background in that.
Okay.
Can you come over between the white lines there? Yeah, come on, this white line and that one there.
Okay, good. So, my name is Bernhard Schott. I joined Adaptive Computing by January this year. And the 12 years before, I was with LSF. Can I have the slide before, please?
Sure. Let's see.
That one. And laser pointer. Mm-hmm. So the LSF solution is often in marketing as, oh wow, you have 100 servers and you can do 99 failovers. Okay, that is technically correct, but kind kind of misleading. Because, yes, you have a mechanism here that scales to not machine 1 and 2, but to n machines. That's correct. But it doesn't solve the issue of the data of the database. So if you think of machines so unreliable and daemons so unreliable that they crash and you need more than a second machine for failing over. Okay, but what about the database? Now, the replication mechanism, and you will be talking about replication mechanisms a little bit later. First of all, there is none. Second, there is one that is asynchronous. Why? Because, and that's something you will mention also later, synchronous replications take time and slow down the performance. Now, when you have an asynchronous replication, you may end up with not complete replicated database in the case of crash. And I have spent time on customer situations where we didn't make it working anymore. So whoever tells you about the wonderful n-1 failover capabilities, have in mind, yes, it works for the daemon, but not for the database. Make sense? Okay, thank you.
Thanks, Bernhard. The real moral to that story, I think, is just that you have to be aware in any of these recipes that I'm going to show you of what are the weaknesses of them. And there are weaknesses in practically any story. None of the things I'm going to show you today could survive the meteor that killed the dinosaurs. Sorry, folks. So you kind of have to understand what are the weaknesses and be prepared to plan around them. Okay, so let's go on to another recipe. This is what I call standard pairwise HA. This recipe, I think, is going to be a good one for many of you. This uses, but not all, this uses twin head nodes. All of the daemons that are part of the stack would be on each head node, and so some of you are already probably saying, well, that's not going to work for me. That's okay. It's a hot-cold kind of a deployment, so daemons are inert on the fallback system, meaning they're not running at all. It uses heartbeat and Red Hat clustering to detect failover events and signal about them. And it uses a replicated file system, and DRBD is the mechanism that I would recommend that you build on for that. So this is what one kind of a standard pairwise HA deployment might look like. You still have the virtual IP or load balancer that's fronting the system. You have your two machines. You now have a Linux heartbeat service that's communicating between these two machines, detecting whether there's health on each side. And you have a replicated file system. You notice that these daemons over on this side are grayed out because they are not running. Okay? And this triangle represents MAM being an optional component. I maybe should have made Torque optional for those of you who are thinking about building a cloud version. A lot of you might not use Torque in the cloud. But anyway, you have whatever the components of the stack are duplicated on both machines, and they're all active on the primary node and all passive or all turned off on the secondary machine. And then you depend on the file system replication capabilities to transfer stuff. The replicated file system is mounted on the active machine, and it's just a device, a block-level device on the machine that's inert. And so what happens is if the heartbeat ever says, oh, wait a minute, he died, then machine 2 starts to activate. And the first thing it does is it mounts the file system. Once the file system's been mounted, it activates the daemons in exactly the same order it would activate them if it had just been booted. And so machine 2 goes on its merry way, and machine 1 can, take its own sweet time getting back to normal. Now, probably there's some obvious flaws in this particular deployment too, for some of you. Some of you, your use cases will actually be well handled by this deployment. But here's some of the things to think about with this recipe. On the good side, all of the services that you're dealing with fail over the same way. And that elimination of complexity can be a really important benefit. If you've ever rolled up your sleeves and built one of these kinds of things, you know that the complexity can be pretty daunting. The heartbeat mechanism that we're talking about here is very well understood. It's industry standard. There's lots and lots of articles on the web about how to deploy and tweak heartbeat. People that you hire, consultants that can help you build heartbeat-based failover are very easy to find. And your file system, yes?
Sorry, when you say heartbeat, are you referring to it in a general sense, or are you referring to a particular implementation?
There is a specific service. Okay, yes. So the question was whether heartbeat is a general description of a service or is a specific service. There's a specific service called heartbeat. If you go out to linux-ha.org, you can read about it, or if you read online in the Red Hat Cluster Suite documentation, you can read about that service. And the white paper gives you some hyperlinks where you can learn more about it as well.
But this is apart from CoralSync, for example.
This is apart from what?
CoralSync, for example.
CoralSync. I don't know. I'm not familiar with that, so I see some nodding, so yes. Okay. And the file system in this picture that we've drawn can't be a single point of failure because it's replicated. That's nice. Now there's some cons to this deployment though. The first one is that this is vulnerable to what's called a split brain scenario. Now, for those of you who don't eat and breathe HA, split brain scenario is a scenario where both machines think that they're the master. And it typically would happen if the heartbeat service right here sends a false signal. Maybe a network router fails, for example. Something that's routing the packets on that red line fails. So now the heartbeat service over here says, well, I'm not getting any evidence that machine 1's alive, so it activates this guy. But the network out here and the network right here are still alive, and it turns out machine 1 is still alive, and so machine 2 is activated in false mode, so to speak. That's the split brain scenario. Now there's some things you can do to protect yourself from the split brain scenario in this. Depending on how you do the mounting of the file system, that can be helpful. You can say, for example, only succeed in mounting the file system if I can prove that nobody else has it mounted, and so forth. So there are ways that you can work around this, but you need to be aware that that split brain scenario can happen. There's more learning curve to build this deployment, and this has quite a bit more complexity than the first recipe we showed you. I think that complexity is well worth it in many cases, and I think for many of you this would be a good solution. But there's reasons why you might not pick it too, which are on that con list. Any questions here?
Just one comment. We're doing sort of a munge of both of them because we sort of figure software's going to fail first, so we'll run active rather than active on. Just because.
Yeah, and that's an example of where you're tuned into a good business requirement that tells you the best solution is run active, and that's great. Let's talk about a third recipe. This is pretty similar to the previous one. I named it the shared pairwise HA instead of the standard pairwise HA because this is a little bit, well, you'll see in a minute when I show you the diagram. So what are the ingredients of this recipe? Well, we still have twin head nodes, all daemons. So those of you who are waiting for me to give you one that doesn't have that characteristic, hold on. This is hot-warm. Some of the daemons might be inert, and some might actually be running but idle on a fallback server. We still use the heartbeat mechanism that we were talking about before. We may introduce database failover techniques, and now we're using a shared file system like GFS or Lustre or something like that. Okay, so what does this actually look like? Well, the top part of the diagrams really hasn't changed much. You still have something that fronts the two machines. You still have the Linux heartbeat. There's a little bit of a difference because now you're seeing things like the RDBMS that's running MAM. You're seeing a Mongo database instance if you're running the solution database and so forth. But what's really different is the bottom of this diagram. So here we're back to a shared file system like we were in the first recipe. All of the database technologies are persisting their data to the shared file system. And now look up here, you see this is variant 1. I'm going to show you a second variant of this same idea, and then I want to talk about what they have in common and how they're different. So this is the variant. Let me flip back and forth for a second so you can kind of see what's changing. In the variant, the databases aren't storing their data in the shared file system. They're storing their data on the maybe direct attached storage for machine 1 and direct attached storage for machine 2, or I guess you could do it to network shares, but the network shares would not be the same shared file system world that we're talking about down below anyway. And in both cases, you have the heartbeat still running, and you're depending when the second machine activates, the configuration files and so forth are found in that shared file system. This variant here, variant 2, shows the introduction of a Mongo arbiter. That would be like a little mini VM that's just running a service that checks the health of Mongo itself. So this is a redundancy with the Linux heartbeat. You're using the database features themselves to do their own replication and their own failover. Now, why would you want to do that? Remember our discussion about the split brain scenario? Well, if you have a redundant signaling mechanism, then when this mechanism tells you, hey, looks like things are not healthy, you can consult a secondary mechanism and say, what do you think? And if this secondary mechanism follows different network paths, then the chances of them both going down at the same time are low. And so this adds complexity, but it gives you some extra comfort that you're not going to have the split brain scenario. And another advantage that's not obvious here necessarily, all of these are shown as being grayed out on the machine 2, but you could actually have, depending on how you configure your data, depending on how you configure your database, you could have some of these daemons actually running and idle, which decreases your failover time. So when you actually get the signal, instead of starting the daemon and waiting for it to initialize and do all of its other fun stuff that it does for 30 seconds, it's already up, and you just have to tell it to activate. Okay, so what's good about this and what's bad? Well, this solves a split brain scenario, as I said, and it may have slightly lower latency. The cons, greater learning curve again. We're still walking up the learning curve here, and more complexity. My experience with this particular one is in very large public clouds. This is often the deployment that, or some variant that's pretty close to this is what gets built. Okay, let's talk about the last recipe, advanced HA. Now, I call this a recipe, but this is a little bit of a misnomer because all of a sudden, this is kind of like really wrestling with the complexity yourself. You have to solve a lot of problems, but you get a lot of power. You know, it's kind of the Spider-Man with great power comes great responsibility kind of a deal. In advanced HA, you can split every service onto its own dedicated box. You still pair daemons, or you can N ways, you can configure them with N backups or whatever if you want. You use the database failover mechanisms for all of the database components, and you can use either replicated or shared file systems. Now this is a very simplified diagram because if I tried to give you a diagram with the amount of detail of the other ones for the advanced scenario, you would quickly get lost in the details, and so would I. But conceptually, if you have the portal, then you have at least 2 instances of the portal. If you have the web services, you have at least 2 instances of the web service. And you see each of these is fronted by either a load balancer or a virtual IP address or something that lets every layer in the stack see the other layers without depending on which specific machine is servicing them at any particular point in time. You could consolidate these. You could say I'm going to put viewpoint and MWS on one box, and so this line and this line collapse into one. You could put MAM and PBS server on boxes together if that's convenient for you. The typical consolidation pattern that we recommend is put web server stuff on one box, which would be MWS and viewpoint, unless you want to put viewpoint outside a firewall. Then put database stuff on another box, and then put application server stuff like Moab and Torque on another box. So that's the basic pattern of advanced HA. We don't typically try to document this because there's so many variants to it that it gets to be a little bit impossible to explain in a lot more detail than what I've explained here. You explain the general concepts, and then you have to dive into the specific constraints of your environment to know what's the right way to do it. Now, the benefits of this, you can meet some very aggressive SLAs with this. You can, if you need to, build an environment where the end user never knows about failover, so to speak. You can tailor how the failover happens on one kind of machine versus another one. You can fine-tune things. The cons of this are that really it's a major implementation effort. And it requires significant learning, and I want to highlight this last word, monitoring. After you build this kind of an environment, you still have to babysit it. You have to test it periodically to make sure that it's up and running. Now that's true of all of these systems, but it's especially true of this one. I'd like to make some general observations. This is just things to know about HA in general as it relates to the Moab stack. I started to say this on the last slide. It's important that you audit whatever you build. So that would mean that if you say, I've built something that can handle a power outage, every once in a while you need to go pull the plug or flip the switch and see if it can handle a power outage. None of these recipes are oriented towards super fast failover. And my background in enterprise software and backups and so forth, when I say super fast failover, I mean millisecond style failover. Some banks have that kind of SLA where they say, look, if it's longer than a millisecond of interruption to the service, it's unacceptable. That's not what we're trying to do here. So most of these recipes will give you failover in a few seconds. When I say a few, I mean like 30, 60, it depends a little bit on how big the machines are, how many clients you're thinking you're going to have to service at once. You may have some of the experience that slide way back at the beginning about downtime where you say very quickly you get to where some new submissions can be serviced, but the full workload of submissions is delayed a little bit. You have to test and find out. But we're not after super fast failover here. Every one of these deployments has security implications. Because you're introducing multiple ways, let me flip back to one of these diagrams, doesn't matter which one I pick. There's suddenly more than one way that you can talk to the system. There used to be one viewpoint box, now there's 2 viewpoint boxes. This particular load balancer could be co-opted or fooled. You could fool the heartbeat mechanism. You're creating attack surfaces. And my time at Symantec tells me that attack surfaces are one of those things that sooner or later get exploited. And so you need to think about the security implications of any of your HA deployments, hopefully you can, put a circle around your deployment and say, inside this fence, we trust things quite a bit more. But I wouldn't recommend that you do that as a general rule. That's a little bit too trusting. Also, these HA deployments are not performance enhancers. All of the recipes that I just showed you show a live environment and an offline environment to some degree of offline. And that offline environment, because it's not actually providing active horsepower, is not making your main environment faster. That doesn't mean that you can't enhance performance in conjunction with HA. It just means that that's not an automatic gimme that as soon as you do HA, you got better performance. Okay? It's also not a scalability enhancer particularly. If one of your head nodes could handle, 50,000 jobs an hour, and now you make it part of a paired HA deployment, well, you're not going to suddenly get 100,000 an hour just because you did that, right? And it's also not disaster recovery. This is part of a disaster recovery scenario or planning, but disaster recovery includes many things besides just straight HA. So, if you'd like more information about this topic, there is a white paper that's available. It explains in a little bit greater detail, and it gives some hyperlinks to specific resources that will help you, for example, learn about heartbeat, so forth. That URL is off of www.adaptivecomputing.com. You can download the white paper there. There are a couple of parts of the appendix that are draft status on this white paper. I wanted to be done for the presentation today. The body of the paper is fine, but you'll see there's a place in the appendix where it's marked as a draft. So feel free to email me if you'd like in a week or two and say, do you have a non-draft version of that? You can also come up and pick up, for the first few people that come up, there's a print version of that white paper here. The documentation for the Hopper release, which is, as we speak, winding its way through the final throes of the release fun, is going to include a task guide for the simple built-in HA topic. That was the first recipe that I talked about. So there's a kind of a how-to on Moab and Torque if you'd like that. The white paper is really the source for documentation for the more advanced recipes. With that, I'd open it up to questions if anybody'd like to explore more.
Just a question. You have load balancers moving stuff around. We just have the submission posted with two server names, and if one's down, it goes the other. So server name equals number one or number two kind of thing.
Yes.
Are you recommending doing load balancers, or?
There's not any particular reason to that I would say yes, you must use a load balancer. There's some benefits to using load balancers. But you can certainly accomplish what you're doing just fine that way. That's what I'm calling the virtual IP strategy, right? Where you have either a virtual IP or a virtual host name. It's the same kind of a thing. The software is mapping to one or the other, right?
We don't do that. We just, if one's down, it'll go to the other. Because you can define in Moab and Torque that there are two Moab servers, two Torque servers. But the only thing that we have an issue with is when it does fail over, you get some extraneous error messages that would bother end users kind of thing. So.
Yeah, depending on how the failover happens and how you have it configured, it's possible for the failover to either be fairly clean or to be a little bit messy and worrying. So that's one of the things that you have to drive out as you test and get comfort. Okay, this warning doesn't matter to me. That one's okay. Or no, I should really be concerned about this during failover. Other questions?
Are you working with anybody that's actually has implemented this right now?
Are we working with anybody that has implemented this? Yes. Let me go back to the list of recipes and talk about them for just a minute. So, simple built-in HA, I'm aware of a number of people who've done that one. Standard pairwise HA, yes. I was on a support call with some folks 2 or 3 months back that were basically going down that deployment route. shared pairwise HA, that section of the presentation comes from our professional services experience with, I don't know if I can name the people, but there's a large bank in Asia that's using shared pairwise HA style deployment, and professional services has built several things that I would classify as advanced HA. Go ahead.
I guess I've missed it maybe in the documentation. I'm not really aware of the support built into Moab and or Torque to support this kind of failover at the software level. It seems to me like, I mean, you talked about inert daemons or inactive daemons. It seems to me like, you know, there's a PBS server running on one machine and you can move it over to another machine, but this idea of having a running PBS mom on one machine that's not doing anything, and the active PBS mom on another machine that's doing all the work, and somehow shifting the load.
So
Where can I read about that?
So the comment is that this idea of the simple built-in HA is unfamiliar, and where could we find more about that in the documentation? There's actually documentation about that that's published right now. The version of the documentation that's coming out with Hopper, I think, is a little bit better because it's task-oriented, but I can give you a link if you'd like to come up after. I can show you where the links are for Torque and for Moab. And it's actually mentioned in the white paper. There's a specific link it gives you. Other questions? Go ahead.
Are the updates to the Moab checkpoint files atomic? If I start writing it out and the master dies on Moab, will the client will the second server be able to pick up the last checkpoint, or will it get
Yeah. So the question is, are checkpoint files written in an atomic manner, or perhaps another way to say it is, could checkpoint files get corrupted? The way that checkpoint files get written is we open up a temporary file, we start writing data to the file. When we've closed the file, we rename it to be a checkpoint file. So the rename operation at the end is the only possible way that something could not be atomic. And depending on your file system, almost all the file systems that I know of would guarantee that rename is an atomic operation. That doesn't mean that it's impossible to have a corrupt checkpoint file, and the reason is that although the checkpoint file might completely describe an application state and might have been written correctly, it's possible that the application got in a bad state before it started writing the checkpoint file. That's a whole separate issue. But the issue that you were talking about, which is, can the checkpoint file be written reliably? The answer is yes. It will always be. It will have self-integrity. Does that make sense? Other questions?
Sorry, got another one. Is there any logic built into, if you go back to any one of the diagrams, is there any logic in Moab to see if the Moab, the disk files on Moab are being updated by two things? If the scenario exists where Moab is, yes, we have Heartbeat, but if Heartbeat doesn't work, if you have Moab 1 and Moab 2 writing to the same shared directory, is there any logic to protect that?
Okay, so the question is, does Moab do anything to guarantee that it doesn't have two active writers to the same files, basically? Is that a fair summary?
Yes.
So the answer is Moab does some things, but it's probably something that could be better. I would punt a little bit by saying that in a case like, let me see if I can get this next diagram, like this one, the reason why we haven't gone down that road more deeply is because we want, like, the replication mechanism here and the mounting mechanism that machine 2 uses can drive that problem out of the equation independent of Moab. So in the case that we would recommend for this particular diagram, we'd say configure DRBD in such a way that only one client is allowed to mount it at a time. And if you do that, then it's impossible for a second Moab to be writing to it. The replication, of course, means that the bits would never be duplicated anyway, but basically DRBD would refuse to replicate something that's not mounted. Does that make sense? So there are several mechanisms you can use to make that issue go away. The Moab mechanisms there are some. Moab does do some sanity checks, but I think that I could imagine scenarios where you could circumvent those checks. So I'm not trusting them wholeheartedly.
Okay. One last question. So the live, can you configure heartbeat to monitor Moab if the Moab service is responding?
Can you configure heartbeat to monitor whether the Moab service is responding? Define which kind of response you're looking for.
Very simple. If the client, if you didn't run MStats,
Yes, you can configure heartbeat. I believe that it's actually quite common to write a script that does an arbitrary command as a way to verify aliveness. And as a matter of fact, I know at the Torque Fest yesterday we were talking about the node health check stuff that's part of Werewolf. That same kind of mechanism would be a smart way to deploy heartbeat so that you're testing the health of your machine in multiple ways. Not just whether the operating system is on, but perhaps whether it can see the DNS server and all these other kinds of things. Other questions?
Just to add to the heartbeat thing, we implemented more for a Apache load balancer with heartbeat.
Mm-hmm.
And we use it to monitor each of our Apaches and steal the virtual IP to the other side if it goes down. So it's very configurable. Anything you can think of in a shell script you can do.
Yeah, great. Thank you. I think that the heartbeat mechanism and the Red Hat clustering and the DRBD, each of them is a very powerful tool. And that's why you see them showing up in 3 of these recipes. They really provide an excellent way to solve the problem. They have their flaws, they have their warts, but I think you can achieve wonderful SLA conformance and a lot of sleeping at night kind of state to your system if you do it right. Hopefully also you feel like it's a little bit demystified. This isn't black magic how you do this. It's very achievable for anybody who wants to spend a little bit of time. Okay, thank you very much.